In today's video, I would like to introduce a very nice problem regarding arithmetic and number theory. Here is the following setup. Find all n as a natural number satisfy this following statement. So we get 7 divides 5 to the n plus number 1, or 5 to the n plus number 1 is divisible by number 7. Okay, we have been asked to determine all the appropriate values of n in order to make this statement true. Okay, so let's link this one right away to the chart. Okay, because the chart is going to give us a nice and real image to find those values of n as a natural number. So before we do that, let's express this one as a divisibility property. Now we will have the following expression. We say in 7 divides 5 to the n plus number 1. This one equivalent 5 to the n plus number 1, which equals 7, is multiplied by k. What is a k? Is a some natural number. Okay, now let's reduce this one to the mod 7. So I get the following. So I get 5 to the n plus number 1, which is congruent to 0 mod 7. Okay, now let's move over this number 1 over to the right of the congruence. So I get 5 to the n, which is congruent to minus 1. We know we can add 7 on both sides, which means I will have 7 minus 1, which is 6. This one will be congruent to 6 mod 7. I have extracted this nice statement. Now let's link this statement to the chart. Okay, then to see. So by using that chart, we are going to find all the possible values of n in order to make 6 as a remainder when you divide this one by number 7. Okay, so let's do that. Now let's go through the chart by using the chart. So here is the following chart. N, we get the following values n. So I'm going to reduce this one to the mod 7. It's more clear. So we get following values 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I'm going to stop here. It's enough. So let's take the following values. This 5 to the n, 5 to the 0, which is 1, 5 to the 1, which is 5. 5 squared is 25. 5 squared is 25. 25 is 4 more than 21. So I get a remainder 4. So 5 cubed. 5 cubed is going to calculate this way. 5 cubed equals 5 squared is multiplied by 5. So we know 5 squared is 4. Just simply multiply 4 by 5 is going to give us 20. 20 is 6 more than 14. So I get a remainder 6 here. Okay, let's change the color to this one. Let's change the color of this one. Next value, just keep multiplying this remainder by 5 in order to get the next remainder. So 6 is multiplied by 5 is 30. 30 is 2 more than 28, because we know 28 is divisible by number 7. So get a remainder 2 here. So for 5, simply multiplying this remainder by 5 is get 10. 10 is 3 more than 7, which is the remainder 3. For the next value, multiplying 5 by 3 is going to give us 15. 15 is 1 more 14. 1 more than 14. For 7, just multiplying 5 by number 1, I get 5. So I get a remainder 5 here. So for 8, I will have the same thing. 5 is multiplied by 5 is going to give us 25. 25 is 4 more than 21. Get a remainder 4. For 9, 4 is multiplied by 5 is going to give us 20. 20 is 6 more than 14. I get a remainder 6 here. So if you take a look at this pattern, if you take a look carefully at this chart, we get number 6 as a remainder at 3 and 9. Okay, so also at 27 you get 6. At 81 you get 6. So this one, it looks like he's going to give us 6 as a remainder at the power of 3. Okay, so how to prove this one generally? Okay, we are going to prove this one by using induction hypothesis. So the base case, we already proven that by chart, taking number 3 or 9 as a base case. Let's claim 5 to the n is congruent to 6 mod 7. This one implies n is going to give us 3 to the k where is k is super equal to 1 as a natural number. Okay, so let's assume this one is true. Okay, always we have a remainder 6, 5 to the n. We have the solution n equals 3 to the k as a solution, where is k is super equal to 1 as a natural number. So we need to prove n equals 3 to the k plus number 1, where is k is super equal to 1 is also a solution. Okay, because as you change in the value of k, you get the power, you get the more solutions as a power of 3. Okay, so let's use this fact. Okay, by using this assumption, then we'll prove this one. Okay, so we get 5 to the n. I'm going to replace n with 3 to the k, so we get 5 to the n, which is congruent to 6 mod 7. It's equivalent 5 to the 3 to the k, which is congruent to 6 mod 7. So what to do here, I'm simply going to raise number 3 as a power on both sides. So I get the following. So I get 5 to the 3 to the k, all is raised to the 3, is congruent to 6 to the 3. We know 6 to the 3 is congruent to 6 square is multiplied by 6. We know 6 square is 1, is a remainder of 1, is multiplied by 6, which is 6 mod 7. So for this one, so I get 5 is multiplied by 3 to the k, which equals 5 to the 3 to the k plus number 1, which is congruent to 6 mod 7. Okay, so let's replace this one with a value n, since we get this one exactly that we have here as an assumption. So this one implies n equals 3 to the k plus number 1. Okay, now we using this assumption exactly, starting with this one by using this assumption. So I get by replacing n with its value, which is 3 to the k, then reducing the equation to the mod 7. At the end, we found 5 to the 3 to the k plus number 1, which is going to be replaced with n, which we have here, to make the equivalence between this equation and this equation. This equation exactly this one by replacing n with its value. So this one always is true. Okay, so which means this assumption is true. Okay, so we have proven this one. So the solution for this equation exactly must be this one, n equals 3 to the k. So I have done this problem. Thank you for watching. I will see you next video. Bye.